through the hypsometric equation, what we know is that the depth of the atmosphere between two pressure surfaces is inversely proportional to the temperature of that temperature, the temperature of that atmosphere. And so that tells us that actually in cold air there is a lesser change in elevation between two pressure surfaces than in warm air. So in this theoretical example here, we have cold air on the left, we have warm air on the right. Initially, we have, and on this graph, we have these 1, 2, 3, 4, 5 different pressure surfaces. Initially, the pressure surface at the bottom here, we have no gradient or no slope between the warm and the cold air. But what happens is as we go higher and higher up to different pressure surfaces, the slope between that warm air and the cold air increases. And so as this gradient increases as we go up in the atmosphere, that ends up being pretty important for developing, number one, the thermally direct circulation, and then number two, the response to that thermally direct circulation with the Coriolis force, which is the geostrophic wind. So those are some concepts that we'll be introducing next. We'll first start off by looking at a map of 500 millibar geopotential height, and this is about halfway through the atmosphere, given that the surface mean sea level pressure is around 1,000 millibars. And this is showing us a map, and the colors here are showing us the elevation of the 500 millibar height surface, and these are in decameters. So we have the blues here are showing us heights of around 5,200 meters, and the orange colors here are showing us heights of around 5,800 meters. So going back to the relationship between the temperature of the air mass and the height of the 500 millibar surface, that tells us that we have relatively warm air both south, both as we go further towards the equator, which is sort of a no-duh. But in this particular example, we also have relatively warm air across much of the western United States. And correspondingly, or conversely, we have relatively low heights or cooler air here across parts of New England and the eastern United States. And so this is part of a ridge trough couplet or a wave. And across the mid latitudes, we actually see lots of these waves, and they end up being the dominant factor of circulation in mid latitudes. The other interesting thing that I'd like to point out here is where we have strong gradients in the height field. So where we see this strong contrast or gradients, which are really defined by a change in a substance over a change in distance. We see these strong gradients here across, say, parts of Illinois and Tennessee. And in those areas, these strong gradients become important when we talk about the geostrophic wind. And what we'll find out is actually the strength of that gradient determines the strength of the geostrophic wind. And also, the geostrophic wind tends to blow parallel to these height lines, isoheight contours. So the pressure gradient force is something that is present. It's basically arises when there is an imbalance. In this case, we can think about the imbalance being high pressure off to the left and low pressure off to the right. Or if we want to do this on height surfaces, say, for example, on the 500 millibar height surface, we could have higher heights to the left and lower heights to the right. And the pressure gradient is always directed down gradient from regions of higher pressure or higher heights to lower pressure or lower heights. And the gradient is proportional, the pressure gradient is again proportional to the difference in pressure or height over a distance. So these lines here represent iso lines of pressure, and you see relatively large spacing here on the left-hand side, and hence we end up developing a weak pressure gradient and weak winds, versus on the right-hand side we have the lines being tightly packed and we have a strong gradient and strong winds. So we put these concepts together and we can think about an idealized Earth, and this Earth has no spin, there are no continents. We have this disproportionate heating, or we have an energy imbalance where we have a surplus of energy in the tropics and a deficit at the poles. And we'll start this circulation off by assuming that air near the surface near the equator is going to warm pretty dramatically and it cools near the poles. And also the idea being that where we have warm air, the air becomes very buoyant, wants to rise, and where we have cold air, the air is dense and wants to sink. We'll start off by a simple example, and this is an example that we see, for example, in a sea breeze circulation. At larger scales, we see it in the monsoonal circulation. In this example here, we apply equal solar radiational heating to both a land surface and a water body. And because the specific heat is much higher over water than it is land, what that means is that the land surface will respond much quicker to a heating imbalance. And so by quicker, I'm actually referring to the temperature will change much faster over land than it will be over water. And as the pressure over land as the temperature over land increases, that allows the air to become very buoyant. The air will start rising, and ultimately your geopotential height fields will actually be much higher aloft over the land than they will be over the colder and denser air over the ocean. So that'll set up this circulation, which is what we call a thermally direct circulation. That being, it's doing the job of taking um, energy from areas where there is a surplus, a relative surplus in this case, where we have the warm air over the land, moving that offshore and bringing colder air over the ocean onshore. So we developed this onshore flow, a monsoonal flow, and what we have is a thermal low over the land and a thermal high over the ocean. So thermally direct circulation is doing the job of trying to eradicate that energy imbalance. So we can apply that to the larger scale circulation, the hemispheric scale circulation, and we get this one cell thermally driven model of global circulation. And the idea here is that we have warm air over the tropics, where we have warm air, the air is rising, piling up, and that air is then transported poleward. And at the pole, we have cold air, air is dense, it's sinking, and this is the exact same idea of a thermal circulation. We're transporting air from areas of surplus to an area of deficit. Okay, so this is accomplishing the goal, right, of that energy imbalance. It's trying to eradicate that energy imbalance. However, it only works on a planet where there's either all land or all ocean. The sun is always over the equator, and the Earth is not rotating. So this is what we call the Hadley circulation in an idealized planet. Now, the additional complication is due to the idea of the Earth actually rotating at different rates depending on latitude, and that brings us to the notion of the Coriolis force. So we have a monarch, and monarch migration occurs. Monarch habitat changes with the seasons based on food availability. So during the winter, monarchs will overwinter in more southerly latitudes in the subtropics, and for this particular example, near Mexico City, and then come spring and fall, temperatures will actually warm and food sources will become more plentiful and available at more northerly latitudes in the United States. Now, a monarch might just decide that they want to move directly northward in terms of cardinal direction. However, that actually ends up not leading them to their original point they were destined to go. And the reason for that is the notion that we have the Earth rotating at different rates, the solid Earth rotating at different rates under us, contingent on latitude. So we're going to introduce a couple concepts here. One is the Earth's angular velocity, and this is just telling us the rotational rate of the planet in units of degrees per second. Okay, we know there's one rotation of the Earth every 24 hours, so we can convert that into radians per second or revolutions per second. And then there's the second component here, which is actually the velocity of the solid Earth. And that is equal to the angular velocity, but we have to use some geometry and consider the distance between the axis of rotation. And that's equal to the radius of the Earth times the cosine of latitude. Okay, so what we actually see is that this is the solid rotation rate of the Earth, the rotation velocity. It is strongly a function of latitude, and we know that the cosine of 90 degrees latitude is going to be 0. What that tells us is actually that the angular or the rotational velocity at the pole is 0 meters per second, whereas at the equator it's going to be quite fast. In fact, here's the diagram of that. And if you're standing at the equator, you may be rotating one rotation per day, but the actual speed of the solid body is 0. Whereas at the equator, you're still rotating one time per day, but because you're so far away from the axis of rotation, you're rotating at a speed of over 1,000 miles per hour. And that leads us to the Coriolis force, which is an apparent force. It's just due to the differential rate of rotation of the Earth as a function of latitude. And it turns out that the Coriolis force is pretty important for long-range trajectories, including the migration of monarchs, including air travel, including ballistics, and including both oceanic and atmospheric circulation. And in the northern hemisphere, the Coriolis force deflects objects to the right of their intended path, and vice versa in the southern hemisphere. And here's an example of why that is. Again, the same migration route for the monarch butterfly. I have two vectors here that have been somewhat exaggerated. They're showing us the rotational velocity in terms of meters per second of the solid Earth. So at further southerly latitudes near Mexico City, the solid Earth is actually rotating at a much faster rate than at northerly latitudes. And because of the conservation of momentum, because the monarch initially starts off with its own velocity plus the velocity of the solid Earth, as it moves to an area where the rotational rate of the solid Earth is slower, it will actually move to the right of motion. So we get a trajectory that looks something like this. Okay. The only parameter that we really need to define here is something called the Coriolis parameter, and that's really just relating to the, the, the the change in the rotational rate of the planet as a function of time. Okay, so for objects that are not moving, you're not changing location, so there's no Coriolis force. But for all objects that are moving, there is some Coriolis force that comes into play because you're changing your location. And the way that we define this is just the rate of change of the solid Earth with respect to time, and it works out such that the answer is the rotational rate of the planet times the sine of latitude. And for the most part in mid-latitudes, this number is something on the order of 1 times 10 to the negative fourth per second. Okay, so we'll use that Coriolis parameter here in a bit. So the Coriolis force in action looks something like this. We initially start off with a parcel that is exposed to a gradient in this case, a gradient in pressure. So we have high pressure here to the south and low pressure to the north. The pressure gradient force is directed down gradient from high to low. That's represented by this vector, which is pointing upward. And you can see that it's constantly upward because the pressure gradient force is always the same throughout all of this. As the parcel starts moving, it starts to acquire a Coriolis effect or a Coriolis force. So the Coriolis force is again only acting on moving parcels. It's proportional to the speed of movement, and it's always to the right of movement. So this parcel starts accelerating, and then once it actually reaches a point where it reaches a point eventually where the pressure gradient force, which is again directed upwards, in this case has an equal and opposite force that's balancing it out, which is the Coriolis force directed to the right of motion. When we get to this point, this is called the geostrophic balance, and the resultant wind, which you can see here by this blue vector, is called the geostrophic wind. And the geostrophic wind is always going to be parallel to the isolines of height. We can estimate the geostrophic wind using a set of equations here. And these equations are actually fairly simple in concept. They tell us that the strength of the zonal wind, which is UG, the north-south wind is VG, the strength of the zonal wind is equal to gravitational force divided by the Coriolis parameter times the gradient in height, which is z, over latitude. So this is this parameter here, delta z over delta y. All that represents is the slope of the height surface over